have two types of registers now. We have architectural registers, which are also called logical registers, as seen by the compiler or the programmer. And typically, you do not have the same registers being renamed. So, for example, here I just showed that R4 has been renamed to R8, but usually that is not how it is done. Usually, you have a separate set of registers which are called as physical registers or which are called as rename registers. And these registers are specifically meant only for renaming. So, you do not use architectural registers for renaming. So in the previous example, I have renamed R4 to R8. So both of them are architectural registers, but then that is just for explanation, but that is not how it is done. Usually you have another set of registers called rename registers meant only for the purpose of renaming. And usually the rename register file is larger than the architectural register file. So what is a register file? You have R0 to R32. So this entire set of registers is what is called as a register file. So this is the architectural register file as specified by the ISA and as visible to the compiler and the programmer. Whereas the rename register file is something which is usually done by the hardware and it is not visible to the programmer. So for example, you cannot go and program the rename register file. So if you have, for example, P0 to P32, if these are the rename registers, you cannot go ahead and write an instruction to program this. So what we typically do is have a step called renaming, and then the program will be rewritten to use the rename registers. And then there has to be some kind of a mapping. So for example, if you rename R0 to P0 and R10 to P1, you need to have this mapping stored in some table, and that is called as the register allocation table or the RAT, in which you're going to save the mapping between the architectural register file and the physical register file. So this is the PR and the AR, that's the short form I've used. So the mapping between the AR and the PR are going to be saved in this particular table. So let us now look at how the register allocation table looks like and how we use it to rename the registers. So let us initially assume that this is the table we have. This is the initial state of the RAT, the register allocation table. So by default, I'm assuming that the first index stands for R0, so and the second one stands for R1 and so on. So initially, let us assume that we are in the middle of some execution wherein some registers have already been renamed. So register R0 has taken up the name P0, R1 has taken up P1 and so on up till P6. And the other registers are free to be used for renaming. So let us also assume that up to about P10 have already been renamed and the other registers which are P11, P12 and so on are free for renaming. So now let us look at the first instruction, add R1, R2, R3. So the first thing we do is we look up in the register allocation table. The first thing we look up is the destination because that is what we want to rename. Remember that the issue of write after write dependencies occur because of register reuse at the destination, not the source. We are reusing the registers at the destination, and that is why we are going to first rename the destination. So the first instruction, add R1, R2, R3, we look up the destination. This is R1. We're going to look in the table. The table currently has P1. We're not going to use that P1 because we want to rename this. So we're going to rename this to the next available free register. Let us assume that the next available free rename register is P11. So like I mentioned already, we have two sets of register files, the architectural register file, which is R0 to R32, and we have the physical register file or the rename register file, which is P0 to P32. Let us assume that for now. So since we have already renamed R10 to P10, so that is our assumption. So P11, P12, etc. are free to be used for renaming. So we're going to first rename this destination R1 to P11. So this is now the updated state of the register allocation table. So what do we now do with this instruction? We change it to add P11. And what do we do with R2 and R3? R2 and R3 are not going to be renamed to a new register, but then we are going to look up this table and find out if any other previous instruction has renamed it. Okay, so this is very similar to this particular example. So for example, if we have renamed R4 to R8, then we also need to look up the table to change this R4 to R8, because that is how you have done the mapping. So now what we're going to do is look up R2 in this table. We see that R2 has a new name, which is P2. So we're going to change this to P2. And we're also going to look up R3. It also has a new name, which is P3. Now, how did these two, R2 and R3, get this name P2 and P3? Because there must have been some other instruction before this. So let's assume there was some other register, some other instruction here, something like this, which had renamed this particular destination R2 to P2. So that is how we are getting this entry in this particular rat. So that is our new instruction. So I have a question here, which maybe you should think about. So what if we have R7 here and it does not have any entry in the rat here? What does that mean? And if you do not have an entry here, then what are you going to use in this source? So for example, if R2 did not have this P2 as the entry here, what would you use for R2 here? That is a question which you should think about at this point. So let us now look at the next instruction, which is sub R4, R1, R3. We repeat the same steps. So the steps are written here. Rename the destination. You look up the destination, rename the destination in the rat. You also rename the destination in the instruction. That's the first step. So we go to R4. So this is R4. You look up here. There is some name here. We are going to rename this to the next available free register, which is P12. So we rename the destination in the rat and also in the instruction. So that is the first step. The second step is look up the sources R1 and R3. You will probably appreciate this P11 better here. So first we look up R1. So R1 had an entry previously, which we have changed to P11. So we cannot just use P1 here, because this instruction has a dependency on R1 here, and therefore we need to preserve that dependency because it's a true dependency, it's a raw hazard. We need to preserve that. So we're going to look up R1 and take the name of the latest renamed register, which is P11, and change it to P11. Similarly, you look up R3 and then nothing has changed. It is P3, so you retain P3. So that is how you continue. So you can probably do the next two instructions yourself. You can do and similarly. R6, you give it a new destination, which is P13. R4 is going to get the latest rename, which is P12. And then R8, we assume that it has been renamed to P8. So now what do you do for the next instruction, R4? What would you do for R4? The R4 has been renamed to P12. So you will have to change that name again and change it to the next available free register. So I'm going to explain that in the next slide. So R4, you look up the table. It was P12, so you're going to change it. So every time you come across an instruction, you're going to change its destination register name to the next available free register. If there is no free register available, you have to wait for the free register to appear. So now R4 is again going to be renamed to the next available free register, which is P14. And then the next two, you can do it yourself. And now this is where you will appreciate why register renaming is useful. So we're going to do the same thing for R1. We're going to change its name to the next available free register. I've not shown it here. Now what happens to R4 is you're going to look up the source and change it to P14. And then R5 will be P5. So now let us see what we have done at the end of all of this. So why did we do all of this? Because we wanted to change the name of these two registers because there was a write after write dependency and we wanted to do the register renaming. So at the end of this, what we have done is actually you've changed this R4 to P12 and you've changed this to P14. So basically you've changed the names of these two registers and therefore even if you were to do this out of order write back, so if you now write the pipeline diagram like we did here, let us go back to the first slide. So even if you were to write a pipeline diagram here and do out of order write back, you will not face an issue because we have now renamed all the registers. So the question here can be, why did we rename all the registers? You could have just renamed these two registers because only those were having the issue. But then there is at runtime, so remember this is being done at runtime in the processor. This is not being done by the compiler. So at runtime, it is hard to figure out which ones have to be renamed and not renamed. So therefore, you basically do the renaming for all the registers and for all the instructions. And the next thing to note is that we have only eliminated the write after write dependencies, but then the true dependencies still exist. Like for example, this dependency still exists here. You have renamed R1 to P11, but P11 to P11 dependency still exists. So similarly, this R4 to R4 dependency is still there as a P14 to P14 raw dependency. So basically, true dependencies still exist, whereas the false dependencies have been eliminated by the step of register renaming. So let us look at another example. So I'll do the first step for you and you can do the next rest of the steps. So we have these 4 instructions here. We assume that the architectural registers are R1, R2, R3. Those are the only ones I've used here. And then we have the rename registers, which are, let's call it P4, P5, P6, and P7. These are the free registers because we have already renamed P1, used P1, P2, and P3 to rename R1, R2, and R3, which means that there have been 3 more instructions before this which have renamed these 3 registers. So given that these are the instructions and these are the free rename registers available for you to do the renaming, what would you use? What would be the instructions now after renaming? So let me do the first one for you. So let us first identify what are the raw dependencies and the write after write dependencies. So this is a raw dependence, that is read after write dependence. And then you have the R3 dependence. This is also a raw dependence, but then we are not bothered about read after write hazards because they have to be anyway resolved later. We are only bothered about the write after write dependencies with R1, and we have to be doing renaming such that this write after write dependence gets eliminated. So I've done the first step for the first instruction, which is you rename the destination. That's the first step. So go to R1. This is the rat. Whatever is there, we don't care. We're going to rename that R1 or P1 to the next available free register. The next available free register is P4. So we're going to rename that to P4. And what are we going to do with R2, R3? You look up the table and blindly take whatever is written there. So P2 and P3 are the names for R2 and R3. So blindly take them and that is our new instruction. So we now update the pool of free registers. So what is the next free register available? It is P5, P6 and P7 because we have already used up P4. So now you can do the rest of the instruction. So to summarize the steps, first thing is you do destination rename, update the RAT and update the instruction. Then look up for the source registers in the RAT. If the entry exists, it means that the register was renamed. So here the entry for R1, R2, R3 exists, which means that the register has been renamed previously by a previous instruction. So what does it mean when it says that there is no entry in the RAT? What does this imply? And what register would you use for that particular instruction? So that's something you should think. You probably already know, or I'll give you a hint. So let us look at another example to explain what I just said. So let us assume that there is no entry in the RAT here, in the register allocation table, there is no entry. So which means that P1, P2, P3, all of these rename registers are free to be used for renaming. So now, how would you rename the first instruction? So you have add. What would you rename R1 as? You would rename it as P1 because that is freely available. So you would rename this to P1. And what would you use for R2 and R3? Because there is no name existing here, ignore this. There's no name existing here. So what would you use for R2 and R3 here? This is something you should think about and we'll discuss it later. So to summarize register renaming, I have just done it very briefly. The name dependencies have been eliminated by renaming the registers. Typically, the rename register space should be larger than the architectural register space, but this is again dependent on the ISA and the architecture. And when an instruction finishes execution, the register in the physical register space or the rename register space is first updated. So basically, when you do a write back here, you're going to write back to P4. So remember, there are two register spaces here. This is the R0 to R31 register space, which is the architectural register space. There is another register space here, which is P0 to P31, which is the physical register space or the rename register space. So when you do a write back here, so basically when you do P2 plus P3, you're going to write it back obviously to P4. But P4 is not visible to the architecture or to the user. What the user sees is only the architectural register. So when are you going to actually update R4 from P4? So that's a question. So basically, first thing is you update the physical register space, which is the P0s, and then later on, you're going to write back to the architectural register space. So our P4 is going to write to R4, which is the architectural register, at the time of the last step, which we called the instruction commit. So if we go back to the seven steps that we had, so first at this point, you're going to write it to a buffer and you're also going to write it to the physical register space. So all of this will become clear as and when we look at the superscalar processor. But right now, you should understand that when you say complete, the instruction completes and writes it to the physical register and to a buffer. And finally, it is going to write it to the architectural register, which is our R0s, R to R31, at the time of the instruction commit, or it's also called instruction retire. So that is the last step of this pipeline.